A very different paradigm to inference in graphical models is the use of what's called sampling or particle-based methods. In those methods, rather than trying to manipulate the exponentially or even infinitely large probability distribution as a whole, we randomly sample instances from that distribution and then use those instances as a sparse representation. We can use those instances then to estimate various quantities that we care about regarding the statistics of the overall distribution. Before we show how this is used in the context of graphical models, let's go ahead and see how it's applied in a simple setting.
So first of all, how do we use samples for estimating quantities that we care about? So imagine that somehow, and we're going to talk about how that might happen, somebody gives us, or we manage to construct, a data set D, which consists of a bunch of samples from a distribution P. And for the moment, we're going to assume that these samples are what's called IID, which stands for independent and identically distributed. So that's where the IID comes from. And now let's imagine that we're trying to compute or estimate, and this is all going to be approximate some quantity of the distribution P. And so for the moment, let's focus on the really simple case where we're trying to figure out where these are binary valued random variables. So the distribution P that we're sampling from is one where the probability that x equals 1 is P. And so think of this like tossing a coin. Now, what is a reasonable estimator for this parameter P that we're trying to estimate? The probability that x falls heads. Well, this is a fairly intuitive answer here. This estimator, which we're going to call T sub D, is simply obtained by looking at all of the samples that we got and counting the fraction of ones. And if you think about it, that's a perfectly reasonable approximation, right? Now, more generally, for any distribution P and any function f whose statistics we're trying to estimate, we can approximate the expectation of the function f relative to the distribution P in terms of this weighted average of the value of f on the samples. And this is often called the empirical expectation. So this is how we might, if we had some way, which we have not yet talked about, of constructing or sampling from a distribution, how we might use those samples for approximating various properties relative to the distribution P, whether it's the probability of an event or the expectation of a function. And note, by the way, that the expectation of a function subsumes the probability of an event, because you could also take the expectation, for example, of an indicator function. And that corresponds directly to a probability. So for example, this probability can be viewed as the expectation relative to P of the indicator function representing x equals 1. The function that takes 1 when x equals 1 and 0 otherwise. So let's think for a moment, just to be concrete, about how one might go about sampling from a discrete distribution. So imagine that we have a discrete random variable x that takes on k values, x1 up to xk. And let's assume that each of these has, that xi occurs with probability theta I. And so we have theta 1 up to theta k. How might we go about using computational tools to generate samples from this distribution? Well, most computers give us a random number generator function that generates samples uniformly in the interval 0, 1. And so if we wanted to convert that into something that samples from this discrete distribution, the simplest way of doing that is to basically split up the range and make this point, say, theta 1, this point, theta 1 plus theta 2, theta 1 plus theta 2 plus theta 3, and let's leave it at that. So 4 values of the random variable. And now we use the random number function to sample from this space and say it comes out here. And we basically say, okay, this was the range that corresponds to x1, x2, this is x3, and this is x4. And so since the point fell here, I'm going to declare that my random value is x3. If I sample again, and I sample in this point over here, I'm going to say, oh, okay, x1. So that's how you would use a random number generator to sample from a discrete distribution, something that we're going to end up using a lot later in this lecture. So now that we know how to sample, let's think about how you might, what are some properties of sampling-based estimation? And it turns out that sampling-based estimation has some, what appeared to be initially, some very compelling performance guarantees. So the first that I'll show is something called the Hoofding bound. And let's parse this horribly complicated statement that we see over here. So first of all, let's work from the inside out. This says my estimator, which is TD, remember, this is my estimator for P. And this says is epsilon away, is more than epsilon away from P. So this says I'm badly wrong. My estimator is not close to the true value, which is P. Okay, I'm at least epsilon away on one side or the other. Now notice that this is a property of the data set, the set of samples that I generated. One set of samples is going to give me one estimate, and a different set of samples is going to give me a different estimate. So that brings us to the next layer out, which is this data set is not a fixed quantity. It's sampled randomly from the distribution. And so I might get good data sets where the estimator is close to P, and I might get data sets where the estimator is far from P. So this says, what is the probability of a bad data set or sample set? Okay? So that parses the left-hand side. The right-hand side is a bound on this probability of getting a bad data set, a data set where the resulting estimator is highly inaccurate. And we can see that that probability grows exponentially, shrinks rather exponentially, in the number of samples m. On the other hand, it also shrinks with epsilon. So the lower the tolerance that we have for errors, the higher the probability of making an error of that magnitude. So if we need really, really tight bounds, then we're not going to get that with very high probability. Nevertheless, a probability that shrinks exponentially with a number of samples looks really good, right? The second bound that has a very similar form is the Chernoff bound. And the Chernoff bound has exactly that same composition. So here is our estimator again. And here, this is epsilon away from P, but whereas this was an additive, this is an additive distance, this is a multiplicative distance. So this is P times 1 minus epsilon and is the lower bound, and P times 1 plus epsilon is the upper bound. And once again, this is the probability of getting a sample, a bad sample set. And once again, we have an exponential, we have a bound on the error, which is written over here. And once again, the number of samples appears in the exponent. That makes us happy. We have the same type of epsilon squared term that shows that the dependence on the tolerance that's required. But here we have this one other term over here, which is the actual value P to which we're trying to estimate. So if we can give you a bound on the error that you get, this bound on how far away you are for P, a bound on the tolerance epsilon, and that also a bound on the probability with which we get a bad sample set, can now say for a given tolerance that we want, for a given error probability that we want, that is, if we want to guarantee that we're within epsilon with probability that's greater than 1 minus delta, we need this many samples. And that's fairly straightforward algebra. You simply say this is less than or delta, and then you just take logs and move things around, and it all comes out to be exactly this. And for the Chernoff bound, we have a similar expression, and that gives us exactly that same kind of bound on M as a function of epsilon and delta, and in this case, P as well. So this looks great, right? We can give you give me an epsilon, which is your error tolerance, and a delta, which is the probability with which you're willing to take being wrong. And I can say, if you can only sample this many samples M, then I can give you those probabilistic guarantees. They're not deterministic, but they're pretty solid. Why is this not a perfect solution to our inference problems? Because each of these has significant limitations. So let's think about the first, which is our additive bound. And let's imagine that you're going into a doctor and you're saying, you know, what is the probability that I have some horrible disease? Well, that probability, hopefully for you, is still pretty low. So maybe if you're unlucky, it's, I don't know, 1%, 2%. Well, an additive error epsilon on 1%, the epsilon that you need to get something that's meaningfully bounded when the true probability P is 1%, the epsilon needs to be really, really small. You can't do epsilon equals 0.01 because that could move you up from 1% to 2%, and that's a factor of 2 increase in your probability, and that's something that people really care about, the difference between 1% and 2%. So you would need something that's more like 0.0001 or maybe 0.0001, depending on, you know, how confident you want it to feel. And now this epsilon squared over here is beginning to look pretty scary in terms of the number of samples that are required to get a reasonable bound. Now you might come and say, well, fine, let's use the Chernoff bound because that gives me relative errors on epsilon, right? So now if epsilon is, sorry, on P. So if now P is small, then by all means I can go ahead and just, you know, have it's a multiplicative factor of P, so I can say P plus or minus 1% of P. Well, unfortunately, there's no free lunch because if P is small, notice that it appears here in the denominator, and so once again, we need a number of samples that could potentially be quite large when we're dealing with small probabilities. So the main message from this is that sampling-based estimation is a reasonable thing to do when P is not too small. When P is not too small, this works fine. When P begins to get smaller, the tractability of this is more in doubt. Now that we understand when we might expect this to work, let's think about how we might apply it in the context of Bayesian networks. So here's our little baby network that we've used for the student example. And what we'd like to do is we'd like to generate samples from this distribution. So this is a distribution of, remember, P of D, comma I, comma G, comma S, comma L. And we'd like to sample from this high dimensional distribution, not that high, but still. And the way in which this is done is actually very natural when you think about the sort of causal intuitions or forward flow of a Bayesian network. We start out, say, by sampling the difficulty variable. And the difficulty variable is sampled from this distribution over here, which is 0.6 versus 0.4. And so we use the trick that we showed a couple of slides ago and say it comes out D0. I'm going to write down D0 over here. Now I'm going to sample I, and I'm going to toss a coin with probability 0.7, 0.3, and say it comes out I1. Now I get to sample grade. And because I previously sampled difficulty and intelligence, I know exactly what distribution grade needs to be sampled from. It's the distribution I1, D0. And so I now sample one of the three values of grade from the distribution in this row that I've picked out in the CPD and say it comes out G1. And I proceed to do the same. So S is sampled from this distribution and say it comes out, S0. And L is sampled from this distribution and say it comes out L1. And that's a sample. And I can do the whole thing all over again. And so I can go ahead and erase all of the decisions that I made before. And I can do the exact same thing. So the blue sample might end up, for example, with D1, I1. And now I use this distribution. And I'm going to end up, say, with G2. And I'm using this distribution. And say I get S1. And I use this distribution. And I get L0. And I can use this procedure to generate as many samples as I want using a very efficient forward sampling process where I sample in what's called topological order. Topological means that I start from the roots and go down. And I always sample parents before their children. And so if I want to use this process, which is very naturally called forward sampling, where we say want to compute to estimate the probability of some assignment little y to some set of query variables y, then what we're going to do is we're going to generate a bunch of samples from that basenet, as many as we think is adequate. And then if I'm interested in some particular event, then I simply compute the fraction of my samples, fraction of samples, where y equals y. And I can use that same procedure for computing other expectations. So whenever, if I have any other function of the sample, I can compute the sample, the function on that sample, and then average it out in exactly the same way that we showed on the first slide. And now we can go ahead and apply the bounds that we showed before. So for an additive bound, we have this many samples that we need. And for a multiplicative bound, we have this many samples that we need. And these are just copying over the two bounds that we showed before. So that's great, but that notice gave me queries without evidence. And what do we do if we want to now ask a question not just about the probability of y, but the probability of y given some evidence, e equals little e? Well, so now it's not that easy to sample from a Bayesian network if I have evidence that's not at the roots. If I have evidence that's at the roots, then that's fine. I know the value of that variable and I can just stick that in and ignore it, ignore everything else. But if I have a variable that I observe that's somewhere in the middle or the bottom of the network, then what happens when I get there? Do I sample it? Do I ignore it? I mean, it seems a bit unclear. And so the simplest solution to that, and we'll talk about others, is an algorithm that's called rejection sampling. And what it does is it does the most naive thing that you could possibly imagine. I generate samples from a BaseNet, and then if they don't agree with my evidence, I throw them out. And that course, the remaining samples, so the remaining samples after I throw out all of the ones that are inconsistent with my evidence are actually sampled from the conditional distribution. Because this is the same as basically reducing the distribution to sort of ignore the parts that are not consistent with my evidence. So that's great, because now I have samples from the right distribution. And once I have samples from the right distribution, I can go ahead and compute the fraction where y equals little y, or for that matter, any other expectation that I care about. Good. What's the problem with this? Think about how likely I am to keep a sample. a sample is going to be consistent with the evidence with a probability, which is the probability of the evidence, right? That's sort of the definition. So the expected fraction of samples that I keep is exactly P of E. So now let's go back to, for example, a medical diagnosis setting, or for that matter, the message decoding example that we talked about previously. How likely is your average evidence? So let's think about medical diagnosis. A person comes in and they have their age and their weight and their gender and 32 symptoms and 10 test results and the fact that they went on a trip to Europe last week, and all of these are pieces of evidence. And the question is, how likely is that configuration of evidence? And the answer is vanishingly small. How likely is your random person off the street to exhibit this exact combination? Almost no. And similarly with the message example, how likely are you to get a particular configuration of noisy bits? Well, exponentially small also. So the number of samples needed grows exponentially with the number of observed variables. The more variables you observed, the lower the probability of the evidence, and this is an exponential decay. And so that means that if you observe more than a couple of variables, basically, this is not a good algorithm to use. So to summarize, algorithmically, this is a very simple procedure. It's very easy to generate samples from a Bayesian network, and we've showed how all these pieces fit together. And once you've done that, there's really elegant and theoretically compelling epsilon delta bounds, as we've shown before. But their usefulness, unfortunately, is limited. The additive bounds tend to be useless for low probability events. The multiplicative bounds are not good either because the number of samples grows as a function of 1 over the probability of the event that we're trying to estimate. And all this is completely irrelevant as soon as you have evidence, because as soon as you have evidence, the number of required samples grows exponentially with the number of observed variables, which means this is not a feasible solution for most practical settings. And one final note that's worth highlighting, this is the only case in, I think, the entire section on inference where I talked about Bayesian networks specifically. And that is because forward sampling, unlike any of the other inference algorithms that we are going to talk about, is just not feasible for Markov networks because there's no, there is no notion of starting at the root. There is no root. There is no sort of any variable that you would naturally start with and whose probability you actually know. And so we don't apply forward sampling to Markov networks. And if you think about it, that's a perfectly reasonable. Okay? So that parses the left-hand side. The one minus delta. We need this many. Nevertheless, a probability that shrinks exponentially with the number of samples looks really good, right? The second bound that has a very similar form is the Chernoff bound. And the Chernoff bound has exactly that same composition. So here is our estimator again. And here, this is epsilon away from P, but whereas this was an additive, this is an additive distance, this is a multiplicative distance. And once again, we have an exponential, we have a bound on the error, which is written over here. And once again, the number of samples appears in the exponent. That makes us happy. We have the same type of epsilon squared term that shows that the dependence on the tolerance that's required. But here we have this one other term over here, which is the actual value p to which we're trying to estimate. So if we can give you a bound on the error that you get, this bound on how far away you are for p, a bound on the tolerance epsilon, and that also a bound on the probability with which we get a bad sample set, we can now say for a given tolerance that we want, for a given error probability that we want, that is how this many samples, exactly this, as a function of epsilon and delta, and in this case, p as well. So this looks great, right? We can give you give me an epsilon, which is your error tolerance, and a delta, which is the probability with which you're willing to take being wrong. And I can say, if you can only sample this many samples m, then I can give you those probabilistic guarantees. They're not deterministic, but they're pretty solid. Why is this not a perfect solution to our inference problems? Because each of these has significant limitations. So let's think about the first, which is our additive bound. And let's imagine that you're going into a doctor and you're saying, you know, what is the probability that I have some horrible disease? Well, that probability, hopefully for you, is still pretty low. So maybe if you're unlucky, it's, I don't know, 1%, 2%. Well, an additive error epsilon on 1%, the epsilon that you need to get something that's meaningfully bounded when the true probability p is 1%, the epsilon needs to be really, really small. You can't do epsilon equals 0.01 because that could move you up from 1% to 2%, and that's a factor of 2 increase in your probability, and that's something that people really care about, the difference between 1% and 2%. So you'd need something that's more like 0.0001 or maybe 0.0001, depending on, you know, how confident you want it to feel. And now this epsilon squared over here is beginning to look pretty scary in terms of the number of samples that are required to get a reasonable bound. Then you might come and say, well, fine, let's use the Chernoff bound because that gives me relative errors on epsilon. Right? So now if epsilon is, sorry, on p. So if now p is small, then by all means I can go ahead and just, you know, have it's a multiplicative factor of p, so I can say p plus or minus 1% of p. Well, unfortunately, there's no free lunch because if p is small, notice that it appears here in the denominator, and so once again, we need a number of samples that could potentially be quite large.
The most generally useful class of sampling methods, one that's very commonly used in practice, is the class of Markov chain Monte Carlo methods. And those are methods that allow us to design an iterative sampling process that, through a sequence of steps, allows us to generate a sample from a desired target distribution that might be intractable to sample from directly. So what are these Markov chains and how do you use them?
So a Markov chain is a method for sampling from a distribution P that is intractable to sample from. And so we've seen one example of such a distribution P. If you'd like to sample from say, a Bayesian network where we have some evidence, we don't really know how to sample from that. If you'd like to sample from a Markov network, we don't really know how to sample from that either in general. And so here we have examples of distributions P, and we'd like to come up with a way of generating even one sample from that distribution P. So a Markov chain gives us a general mechanism for doing that. And what the Markov chain does is it defines an iterative process by which the first sample that you generate is not going to be from a distribution P. But ultimately, as you move along, you are going to get closer and closer to generating a sample from P. So let's understand what that means. So we have a Markov chain, and a Markov chain is defined over a state space, which we're going to use X's to denote. And so here is an example of such a state space. This is a very simple state space. It starts with the 0 point over here, and you could imagine, and it has the 4 negative numbers to the left and 4 positive numbers to the right. And a Markov chain defines a probabilistic transition model, which, given that I'm at a given state X, tells me how likely I am to transition to a different state X prime. And that is a probability distribution as indicated in this formula here, so that for any X, the probability, the sum over the probability of the states to which you can transition is exactly 1. So, for example, if in this case we have our little grasshopper who starts out at state 0, we can see that it has a probability of 0.25 of transitioning to the right, a probability of 0.25 of transitioning to the left, and a probability of 0.5 of not making any progress and staying exactly where it is. And in fact, that same general probability distribution is actually in this example replicated across the different states in the chain, with the exception of the states at the end where if the poor grasshopper tries to go to the left when it's at -4, it's going to hit the wall and it's going to end up staying where it is regardless. And so the probability in this case of staying is actually 0.75, corresponding to the 2 different cases that we just talked about. But anyway, this is a Markov chain, and you can imagine simulating a random process by which a grasshopper traverses this chain. And so initially it starts out with, say it's state 0, and then what happens as it moves, it selects to move left with probability 1/4, right with probability 1/4, and stay at the same place with probability 0.5. Once, say it's moved to the left, it now does exactly the same thing. So let's think about the temporal dynamics of this type of process. We can ask what is the probability that at step t+1, so this is the step, what is the probability that at that time step, the state at time t+1 is equal to some value x prime? Now we can get that by a recurrence relationship that looks at the state at time t. So if we had previously computed the probability distribution over where the grasshopper might be at time t, we can sum up over all possible states where the grasshopper might be, and ask if it was at state x at time t, what is the probability that it ends up at being going to x prime. So this together gives me a distribution over pairs x comma x prime, where which measures the probability that at time t the grasshopper is at state x and at t+1 is at x prime. And since I'm only interested now in asking about t+1, I sum up or marginalize the time t step state x. So if we go back to our grasshopper example, we can simulate this process. And here is the first 3 steps of this. So at time 0, the grasshopper is at state 0 with probability 1. At time 1, it's going to be at -1 with probability 1/4, and at +1 with probability 1/4, probability 1/2, it's stuck at the same state. And now we can simulate the next step. So it's at the next time step, the probability that it manages to move all the way to -2 is 0.25 squared, because it considers 2 successful moves to the left. Here you have 2 successful moves to the right. At state 0, you have, for example, a sum of different events, which is the probability that it stayed in the same state twice, so 0.5 squared, plus the 2 events that correspond to moving to the left once and back to the right, or moving to the right and back to the left, each of which happens with probability 0.25 squared. So this is an example of how you would do this. Now, it turns out that for many of these chains, and we'll describe conditions in a moment, ultimately, as the process evolves, the probability distribution kind of equalizes, which means that the probability that at time t you're at state x prime is almost the same as the probability that at time t plus 1 you're at x prime. So sort of the distribution over where you might be tends to equalize. And so we can then consider what's called the limiting process, the limiting distribution that you would get as you simulate the process for more and more steps. And that is typically denoted by pi, which is called the stationary distribution. It also has a bunch of other names, but stationary is the most common. And if you plug in, if you basically take out this approximate equality, and you can see that what we have as a condition on pi is that the distribution at one time step needs to be, the probability of x prime in the stationary distribution needs to be equal to this summation over here, where pi now appears both on the left-hand side and within the summation on the right-hand side. Now, it turns out that this concept of a stationary distribution is actually at the heart of Google's PageRank algorithm. So what they're actually computing, at least in the original PageRank, is the probability that if you take a random walk on the web, that you end up at a particular website. So this notion of a stationary distribution is actually quite powerful, as we've seen. So let's take a simple example, which is this 3-state Markov chain shown here. So for example, note that from state 1, there's a probability of 0.75 of going to state 2 and 0.25 of going to staying in the same state. And we can now write down a set of equations that represent what properties the fixed point distribution needs to satisfy. If you do that, you're going to get the following equations. So for example, it tells me that pi of x1 has to be equal to 0.25 times pi of x1 because of the self-transition here, plus, 0. Yes, sorry. That pi of x1 is equal to 0.25 times pi of x1 plus 0.5 times pi of x3. Okay? Because if you were at pi of x, you can end up in x1 in one of two ways. Either by starting out in x1 and staying there, or by starting out at x3 and moving to x1, which happens with probability 0.5. Similarly, pi of x2, you can end up either by being at x2 and staying there, which is this transition, or by being at x3 and moving to x2, which happens with probability 0.5. And so this is a set of 3 simultaneous equations in 3 variables. This by itself is an underdetermined system because you can multiply all of the pi's by a factor of 100 and it would still be a solution, but we can add to that the one constraint that says that all of the pi's have to be equal, the sum of all the pi's has to be 1, which is because it's a probability distribution. And once you do that, you end up with a unique solution to the system of linear equations. And it's not difficult to plug those pi's into the system and confirm that indeed this is the stationary distribution that satisfies these equations. By the way, for the grasshopper example that we showed on the previous slide, the stationary distribution is the uniform distribution. So this has to be one of the dumbest ways of generating a sample from the uniform distribution, but it does in fact generate eventually a sample from something that's very close to the uniform distribution. So when does a Markov chain converge to a stationary distribution? I said many of them do, but it turns out that not all of them. And so a condition that guarantees convergence to a stationary distribution is something called regularity. So a Markov chain is regular if the following condition holds. And notice the order of the quantifiers. If there exists some number k, integer k, such that for every pair of states, so this is the universal quantifier, the probability of getting from x to x prime in exactly k steps is greater than 0. Now notice what that means. It means that you pick the k first. And so you can't have a different k for different pairs of states. You can pick k to be 1,000 or 1,000,000, it doesn't matter for this purpose, but you need to pick it first, and then there needs to be a way of getting from x to x prime in exactly that number of steps with probability greater than 0. It turns out that that is a sufficient, not a necessary, but a sufficient condition to guarantee that the Markov chain converges to a unique stationary distribution regardless of its start state. So it converges, and it converges to a single stationary distribution that's characterized by the equations that we saw on the previous slide. Now, what are some sufficient conditions for regularity? Because this one is a little bit hard to check. And so one sufficient condition for regularity that people often use in practice is first, that every pair of states, x and x prime, need to be connected with a path of probability greater than with probability greater than 0. For every state, there is a self-transition. So you can always transition from a state to itself. So if you think about that, that means that if you take k to be the diameter of this graph, so if you set k to be the distance between the furthest pair of states, then you can get between every pair of states using exactly k steps, because you can take less than k and then just stick around for a while until you hit k because of the self-transitions. So this is a way of guaranteeing that, that for this value k, you can get from every state to every state. And that's what people typically do. They typically add these self-transitions to guarantee regularity.
So to summarize, we've defined the notion of a Markov chain, which defines a general dynamical system or an iterative sampling process from which we can sample trajectories that traverse the space of the chain. Under certain conditions, such as the regularity condition that we defined, which is sufficient although not necessary, this iterative sampling process is guaranteed to converge to a stationary distribution at the limit, that is, after we generate enough samples. And so this provides us with a general approach to sample from a distribution indirectly, which means that if we have a distribution from which it's intractable to sample, this provides us with an alternative mechanism. We previously defined the notion of a Markov chain that allows allows us to generate samples from an intractable distribution. But we left unanswered the question of, assuming we have a Markov chain that has the desired stationary distribution, how do we go about using it in the context of a concrete algorithmic procedure?
Well, let's imagine that somebody has provided us a Markov chain for a distribution, imagine that our goal is to compute some probability relative to a distribution P. But for whatever reason, P is too hard to sample from directly. And so how do I use a Markov chain to get around that? First, we construct the Markov chain T, whose unique stationary distribution is P. So it needs to be a regular Markov chain usually. And then we're going to generate samples from this distribution. So we're going to start out by sampling my initial state from some arbitrary distribution P0. P0 is not the same as P, so obviously I can't use the zero sample as a way of estimating an event relative to P. And so what I do now is I start walking along the chain, starting sampling xt plus 1 from the transition model. And because the chain converges to a stationary distribution, eventually I'll have a sample that is very close to being sampled from the distribution P that I care about. So now here's the sticky issue, and this is really a sticky issue. When have we walked long enough that we could actually use our samples? Because we don't want to use samples at the beginning because they're far from P. And so we need to walk around long enough for the chain to get close to its stationary distribution. And that state is called mixing. So mix is when P of T is close enough to pi, so that your time t distribution is close to the stationary. And that's the point at which I could say, good enough, I can start collecting samples. So how do we know if a chain has mixed or not? And the short answer is, you don't. And so this is, as I said, the sticky part of Markov chain methods. So in general, you can never really prove that a chain has mixed. But in some cases, you can show that it hasn't mixed. And then if you run lots and lots of tests, and none of them have convinced you that the chain hasn't mixed, then you sort of resign yourself to assuming that it has, in fact, mixed. So how do you convince yourself that a chain hasn't mixed? You compute chain statistics, and we'll show some examples of that in a moment, in different windows within a single run of the chain. So for example, here I have a single run of the chain, and I run for a while, and then I look at little windows. Usually they won't be this small. And I compare this window to this window, computing various statistics. For example, what is the probability of hitting a particular state? And I say, is the probability of that in this window close to the probability of that in this window? And if it is, then maybe I've reached this, at least some kind of convergence point in terms of where the chain is reached. Now, this, of course, is not a sufficiently good answer, because it could also be derived in a chain that has these sort of two very high probability regions that are very hard to get from each other. And if the chain is kind of ambling along in this part of the space and never hitting the other part of the space, then you're still going to get very similar probabilities across a window of a single run of the chain, because all of the samples are taken from this part and none of them are ever taken from that part. And so we don't know that we haven't mixed. So a more reliable statistic is to take these statistics, a more reliable evaluation criterion is to take these statistics across different runs that are initialized in different parts of the space. And then you might hope that one run of the chain is traversing this region, and another run of the chain is traversing this region. And so now the statistics would show a difference and indicate that mixing hasn't taken place. So what statistics might, what might we do it more concretely? So let's look at two examples. Here is two example runs of a chain that we'll describe a little bit later. And what we measure here, and this is the first statistic to measure in Markov chains, is the log probability of a sample. So you compute the log probability of a sample. Now you can't always compute the log probability directly. You might compute an unnormalized log probability, as we'll talk about later. But basically, you compute the log probability or some constant factor thereof, and now you can compare two runs. And this is a run that's initialized from an arbitrary state, and this is one that's initialized from a high probability state. And you look at this and you say, has it mixed? Relative to this criterion, the answer is maybe. It looks okay, but you're not entirely sure. But we can look at other statistics. Oh, sorry, let's look at another example. What about this one? Here is, again, an example of two runs, one of which is initialized from an arbitrary state and initialized from a high probability state. And you can see that the log probability values are nowhere close to each other. And so in this case, the answer is definitely not. These are two runs of the chain, and really neither is mixed. And so you need to run for a lot longer, which, this goes up to 600,000, so kind of indicates to you how much time this might take. A different statistic, a different way of looking at this is for a different kind of statistic. So now we have, for example, the probability relative to a window that we compute in the chain. So remember, all of this is relative to a window in the chain after we hope that mixing has taken place. And now we compute the probability that within states in this region, what is the probability of that the states are in some set. So for example, the set of states where x3 is equal to 2. And now we compute that statistic using the two initializations of the chain. So this is chain 1, or run 1, and this is run 2. And now we do a scatter plot for different statistics. So each of these points, this is the probability, say, of x3 equals value 2. This might be the probability that x1 is equal to 0. This might be some other probability that, x5 is equal to 7. And so each of these is a statistic. And what you see here is a scatter plot. One is the estimate that I get from the one chain and from the other. And looking at this, it should be obvious that this first chain that we have not gotten mixing on the left-hand side, because you can see that there are all these points here that have a high probability in one of the two runs and a probability 0 in the other, and vice versa. Whereas here, most of the estimates are clustered around the diagonals so that you're getting similar estimates from the two chains. And so again, the first one is a clear no, and the second one is maybe. And if I do a lot of these statistics and they all come up with maybe, then I'm willing to trust the answers and assume that mixing has taken place. So now that I've started collecting samples, how do I use these samples? Well, one important observation to keep in mind is that once the chain is mixed, all of my samples are from a stationary distribution. That is, if xt is from pi, so is xt plus 1, t plus 2, t plus 3, and so on and so forth. And so we can use every single one of those samples because they are all from the correct distribution. So once I've determined that I've sampled long enough for mixing, or believe that I've sampled long enough for mixing, we should collect and use all of the samples. And in fact, there are, you might read some papers that say, oh, I'm only going to collect every 100th sample. There's actually papers that prove that using every single sample is better than collecting every 100th sample. But then you might ask, well, why would those papers tell me that I should only collect every 100th sample as opposed to collecting all of the samples if they're all from the correct distribution? Because, and this is undoubtedly true, adjacent samples, ones that are nearby to each other in time, are correlated with each other. Because even if xt is from the right distribution pi, and so is xt plus 1 is still going to be close to t, close to xt. And so you're not really getting two different samples. You're getting two that are very close relatives to each other. Now, as I said, it's important to recognize that phenomenon because it's important to realize that just because you've reached mixing and collected 1,000 samples doesn't mean you have 1,000 samples worth of information. So you shouldn't go back and apply one of the bounds that we saw in assuming you have IID samples. The samples are not IID. So, but that doesn't mean you shouldn't use them. Using them is still better than not. Now, this is where you get bitten twice by the same phenomenon. The worse a chain is to mix, so the longer you need to wait for the initial samples to be good enough, the more correlated the samples are because the slower you're moving around in the space in general. And so if a chain is bad, it's bad in two different ways. It's bad because it takes you longer to mix, and it's bad because the samples that you're collecting are not as useful because of the correlation structure between the samples. So to summarize, first the algorithm and then the implications. Here is how we would actually end up using a Markov chain. So first of all, I'm running C chains in parallel, and I'm going to sample an initial state from each of them. And then I'm going to repeat until I reach some determination that mixing has taken place. And what I do is I forward march each of the chains using a random walk process where I generate the t plus first sample from the tth sample for that corresponding chain. Then I compare window statistics of the type that we showed earlier in the different chains to try and determine whether mixing has taken place. And then I repeat until I'm confident in the mixing properties. With that, I now repeat until there's sufficient samples to collect data. So I start out with an empty sample set, and then for each of my chains, I generate a sample, and I put it in my sample set. And I repeat until I have enough samples. And then finally, when I've collected enough samples, I can go ahead and compute the expectation in anything that I care about, whether it's an indicator function or a more complicated function. Summarizing the implications. Markov chains are a very general purpose class of methods for doing approximate inference in general probabilistic models, not even necessarily probabilistic graphical models. They're often very easy to implement because the local sampling that we're doing is often quite straightforward to execute. And it has good theoretical properties as we generate enough samples that are sufficiently far away from our starting distribution. Unfortunately, these theoretical guarantees are very theoretical in many cases. And so this method also has some significant cons. First, it has a very large number of tunable parameters and design choices. What's my mixing time? Which statistics do I measure? How close are the statistics to each other in order for me to declare that mixing has taken place? How many samples do I collect? What window size do I use to evaluate mixing? All of these are design choices. They all make a difference. And so there's a lot of finicky tuning that needs to be done when running an MCMC method in practice. The second is that depending on the design of the chain, this can be quite slow to converge because it's very difficult to design chains that have good mixing properties. And finally, it's very hard to tell whether a chain is working. That is, it's not straightforward to determine whether the chain has mixed and whether my samples are sufficiently uncorrelated with each other that I'm getting a reliable estimate of whatever it is that I'm trying to figure out. So a lot of advantages, but also some significant disadvantages.
We previously defined the notion of a Markov chain that allows us to generate samples from an intractable distribution. But we left unanswered the question of, assuming we have a Markov chain that has the desired stationary distribution, how do we go about using it in the context of a concrete algorithmic procedure?
Well, let's imagine that somebody has provided us a Markov chain for a distribution, imagine that our goal is to compute some probability relative to a distribution P. But for whatever reason, P is too hard to sample from directly. And so how do I use a Markov chain to get around that? First, we construct the Markov chain T, whose unique stationary distribution is P. So it needs to be a regular Markov chain usually. And then we're going to generate samples from this distribution. So we're going to start out by sampling my initial state from some arbitrary distribution P0.
We defined the notion of a general Markov chain. We talked about how certain conditions guaranteed that if we sample from the chain, we achieve convergence to a stationary distribution. We then described how if we then generate samples from the Markov chain, we can use that to estimate properties of that stationary distribution, like various statistics that we might care about. But the question of where the Markov chain might come from was left very vague. It turns out that for graphical models, people have constructed a general purpose sampler that can be used to sample from any graphical model, and that class of chains is called the Gibbs chain. So now we're going to talk about the Gibbs chain and how it's used in the context of graphical models.
So here, our target distribution, the one from which we would like to sample, is the good old Gibbs distribution P of phi of x1 up to xn. And just as a reminder, that P of phi can equally well represent a Gibbs distribution that we got from just a product of undirected factors, a Markov net style distribution, or it could as well represent a set of factors that we got from a Bayesian network reduced by evidence. So that is the factor set phi, and everything that I'm going to say from now on is agnostic to where those factors phi came from, if it came from a directed or an undirected model. So now our Markov chain state space is a set of complete assignments, little x, to the set of variables, big X. So we're sampling over, note, an exponentially large state space, the space of all possible assignments of the random variables in our graphical model. So those little circles that we saw when we were talking about Markov chains and we were going from one state to the other, each of these is now a complete assignment to x1 up to xn. So it turns out that the Gibbs chain is actually a very simple and easy to understand Markov chain. And here's what it does. Assume that I have a starting state, little x. What I'm going to do is I'm going to take each variable in its turn, using some arbitrary ordering, and I'm going to sample a new value for that variable given values for all of the rest. So let me introduce this notation. This is an assignment to all x1 up to xn except xi. So for example, if we had 3 random variables x1, x2, and x3, we would sample x1 given x2 and x3, x2 given x1 and x3, and x3 given x1 and x2. Okay, so one at a time. Okay, so let me draw that out because in order to make that clear. So here we would have, here's my current assignment. Let's say here's x1, x2, x3, and let's say that we have 0, 0, 0 as my initial assignment. So I'm going to start by sampling x1 from the probability of x1 given x2 equals 0 and x3 equals 0. And let's say I end up with 1. The other two haven't changed yet. I now sample from p of x2 given x1 equals the new value 1 and x3 equals 0. And say that stays 0, because it could. And then I sample x3 from the probability of x3 given x1 equals 1 and x2 equals 0, and say that changes to the value 1. And so now this is my new assignment 101, which gets instantiated into x prime. That is a single step of the Gibbs chain. It goes and potentially modifies, doesn't have to modify because you might end up staying in the same assignment, resamples every single variable in its turn, and when all of them are done, that's my new state. So let's do this example in the context of a real graphical model. So here is the good old student Bayesian network, and I'm assuming that I have observed values for 2 of the variables. So I've observed L equals L0 and S equals S1. And so now I have a product of reduced factors that represent the evidence that I've received. And only 3 variables are now getting sampled because the other 2 are fixed to their observed values. So now I'm sampling from P tilde of phi. I mean, I'd like to sample from P tilde of phi of D, I, G given little s1 and L0. And so what I'm going to do in this sampling process is I'm going to start out with some arbitrary assignment to these three variables, di and g. So for example, since it's arbitrary, d0, i0, g0. And now I'm going to go ahead and sample each of these in turn. And so I'm going to initially sample d from of d given I0, G0, S, L0, and S1. Okay? And we'll talk about how that's done in just a moment. And that might give me D1, I0, G0. And now I continue and I might sample I. So I'm going to sample I from probability of I given D1, G0, L0, S1, and say I end up with I1. Finally, I sample G, and it couldn't be G0, I apologize, because G only goes 1, 2, 3, so let's say it was G1. And now I sample G from the probability of G. Okay, so this was G1 here too. And this is the probability of, I'm now sampling G from the probability of G given D1, I1, because that's where I am right now, L0 and S1. I end up with G3. So my new assignment is this one, D1, I1, G3. So how do I do this in a tractable way? So here's the trick that, I mean, you might say, well, you're dealing with this intractable distribution. I mean, you've just moved the problem from the original problem that we had to computing these conditional probabilities. Why is that any easier? Well, turns out it is. So let's look at the sampling step over here, where I sample xi from this conditional distribution. And let's break that down into these, into its constituent definitions. So this distribution, this conditional distribution, is a ratio between the joint distribution of the value xi and the stuff on the right-hand side of the conditioning bar divided by the stuff on the right-hand side of the conditioning bar. Now, importantly, because each of these is an unnormalized measure divided by the partition function cancels, and so I end up, so if I had a 1 over z here, the 1 over z cancels, and I end up with the ratio of two unnormalized measures. So, and the point being now that this is a complete assignment and therefore is a product of factors. So let's look at that in the context of a concrete example and see how that might help us. So now we're doing an example that's a Markov network in order to demonstrate that this is equally applicable to both. So this is our good old misconception network where we have these 4 factors, phi1, phi2, phi 3, and phi 4. And let's imagine that we're trying to do p phi of A given B, C, and D. And we can see that what we have here is p tilde phi of A, B, C, D divided by the sum over A prime, and I'm using A prime to distinguish it from this A over here just to avoid ambiguity. P tilde phi of sum over A prime, P tilde phi of A prime B, C, D. And now I'm going to, since each of these P tildes is a product of factors, I'm going to inject that product of factors into each of the numerator and denominators separately. And so over here I end up with phi 1 of AB times phi 2 BC, phi 3 CD, phi 4 AD. And similarly I end up with exactly the same form of expression in the denominator, except that I sum out over A prime. And what do we determine by looking at this expression? Well, some things are immediately jump to one's eye, which is that phi 2 BC appears in the numerator and in the denominator, and therefore I can cancel it. And similarly with phi 3 of CD. And so what I end up with here is a product of just two factors, phi 1 of AB and phi 4 of AD, which are the two factors that involve A. Well, that's for the numerator. What about the denominator? Well, the denominator is just our good old normalizing constant. So really what we have here is that this is proportional to phi 1 of A little b times phi 4 of A little d. So this is a factor over A that I can compute by multiplying two singleton factors, in this case over A, multiply them together and renormalize, and I get a distribution over A from which I can sample. And we already talked about how to sample from a discrete distribution. So what is the computational cost now of this algorithm? The sampling step for xi given all of the others is simply this expression over here, which is proportional to a product of factors. And not just any old product of factors, but just the factors that involve xi. Just the factors that have xi in its scope. Which means that I only care about xi and its neighbors in the graph, which for a large graph with tens of thousands of nodes can be a considerable savings. Okay? So only xi and its neighbors. So do we like the Gibbs chain? We've certainly defined it. Does it have the properties that we would like it to have? Well, the answer is unfortunately not always. So let's look at, and specifically, is it a regular chain? Do we have guaranteed convergence to a unique stationary distribution? So the answer is unfortunately not, and to that we're going to return to our old enemy, the exclusive OR network, which, as I said in other examples, is the counterexample to pretty much anything is exclusive OR. So let's look at the exclusive OR network. So here we have Y, which is the exclusive OR of x1 and x2. And let's imagine that I observe Y equals 1. And so these two disappear. And now I'm going to try and sample x1 and x2, which I should be able, if I were so lucky, I would get that each of the two possible states for x1 and x2 occurs with probability 1/2. So let's imagine that I start out with this one, and I'm going to now sample x1 given x2 and y. So I have my initial state is 0, 1 for x1 and x2, and of course y equals 1 is my evidence. And now I'm going to sample x1 given x2 and y, and that is a deterministic dependence, and the only possible value that I get is 0 for x1. Well, am I going to have any better luck with x2? Nope. I'm going to end up with exactly the same 0, 1 that I started out with. Then I can do the exact same thing again, and you know what? It'll work the same way every single time, and I will always end up with 0, 1. Conversely, if I start out with 1, 0, I will never leave 1, 0. So this is a classical example of a non-mixing chain. On the other hand, if all factors are positive, that is, if there are no 0 entries in any of the factors, then you can show that the Gibbs chain is regular. Now, for x1, well, am I going to have any better luck with x2? Nope. I'm going to end up with exactly the same 0, 1 that I started out with. Then I can do the exact same thing again, and you know what? It'll work the same way every single time, and I will always end up with 0, 1. Conversely, if I start out with 1, 0, I will never leave 1, 0. So this is a classical example of a non-mixing chain. On the other hand, if all factors are positive, that is, if there are no 0 entries in any of the factors, then you can show that the Gibbs chain is regular. Now, however, it's important to realize that regular doesn't mean good. So I can make this chain regular by adding a tiny probability epsilon of having y not be the exact exclusive OR of x1 and x2. So now the chain is regular because all possibilities have probability non-zero, and it's still going to mix extremely slowly for values of epsilon that are small. So regularity, remember, is a very weak condition. It says if you sample long enough, we will eventually converge, but it doesn't mean it'll happen in a reasonable time frame. And one such example of a very slow to mix chain actually occurs in practical applications. So here's one example. Here it's an example in our image segmentation domain. And imagine that we're trying to resample, say, the class of, let me use a different color, of this superpixel here, and that we have some fairly strong potentials that tell me that the class of this superpixel should be very highly correlated with the class of its adjacent superpixels because of the appearance being very similar to each other. So I have a pairwise Markov network with some very strong potentials that try and enforce consistency between adjacent superpixels. So if it turns out that for whatever reason, my initial assignment was actually wrong. So for example, what is often an error mode for such segmentation models is that road is often labeled water or sky because the appearance is actually kind of a similar grayish kind of appearance. So say that, for example, if I happen to label all of these superpixels as, say, water, and now I'm going to use Gibbs sampling, none of them are likely to move away from their current assignment because each of the superpixels is really constrained by strong pairwise potentials with its neighbors. And so this notion of slow to mix Markov chains is not just a theoretical construct that occurs with exclusive OR, it actually happens in practice a fair amount. So to summarize, what Gibbs sampling does is it takes the very challenging problem of inference in a Gibbs distribution and converts it to a sequence of easy sampling steps, where each sampling step samples one variable given all of the others. This method has the advantage that it's probably the simplest Markov chain for probabilistic graphical models, and it's very efficient to compute each of the different steps. The cons are that it is actually very slow to mix when the probabilities are peaked and variables are very highly correlated. And it's only applicable in cases where we can sample from a product of factors. Now, we could always do that in a discrete graphical model if our factors aren't too large. But if our samples are, but if we have, for example, either a very densely connected say Markov network, or we have one with continuous distributions where the product of factors isn't something that has a nice parametric form that we can sample, Gibbs sampling might not actually be applicable. And so there's non-trivial limitations to the applicability of Gibbs sampling, and even when it applies, it is actually very slow to mix, and we often want to do something more clever, and we'll talk about more clever algorithms later on.
We define the notion of Markov chain Monte Carlo sampling as a general paradigm for generating samples from a distribution from which it is otherwise difficult or perhaps intractable to generate samples directly. Markov chains gives us a general way of approaching this problem, but the framework leaves open the question of where the Markov chain comes from. That is, how do we design a Markov chain that has the desired stationary distribution? We talked about the Gibbs chain as a general solution to this problem in the context of graphical models, but we also mentioned that the Gibbs chain has limitations in terms of its convergence rates for certain types of graphical models. So what happens if we have a graphical model for which the Gibbs chain doesn't have good convergence properties? How do we design a Markov chain for that? Well, it turns out that there is a general class of methods called Metropolis-Hastings. And the Metropolis-Hastings algorithm gives us a general approach for designing a Markov chain with a desired stationary distribution. In fact, for a given stationary distribution, we can construct a whole family of different Markov chains that explore the space differently, and then try and select among those or construct one among those that has good convergence properties for our distribution.
So the key insight behind the Metropolis-Hastings method is the notion of a reversible chain. So what does it mean for a chain to be reversible? Imagine that we have a chain with a particular stationary distribution pi, and we're going to consider two different experiments. In the first experiment, we're going to pick a point in the space. We're going to, a point in the state space, according to the probability distribution pi. So say we land on this one. And then we're going to pick a random edge emanating from the state that we picked, according to the transition model defined by the chain T. So say we pick this edge. So that's the first experiment. The second experiment is exactly the same thing. We're going to basically do this experiment twice. So now we're going to pick a state, and once again, we're going to pick an outgoing transition from that state. A chain is reversible if when I do this experiment, the probability of traversing this edge, this red edge over here, is in this process is exactly the same as the probability of traversing this green edge in the other direction. That is, if picking I and then traversing to J occurs with the same probability as picking J and then traversing to I. So written in mathematical notation, this tells us that pi of x, which is our red state, times the transition along the red edge is equal to the probability of x prime, that was my green experiment, times the probability of transitioning in the opposite direction. Now, it's very easy to construct Markov chains that are not reversible, so this is by no means a universal property of Markov chains, but it turns out that reversible Markov chains have elegant properties that allow them to be constructed so as to give rise to particular stationary distributions. And specifically, we can show, and it's not a very difficult proof, we'll show it in a moment, that if this equation, which is called the detailed balance equation, if this equation holds, and T is a regular Markov chain, then T has a unique stationary distribution, which we know from the fact that it's regular, but furthermore, that stationary distribution is pi. Let's go ahead and prove this, and it turns out to be actually a one-line proof. So here we have, we take the two sides of the detailed balance equation, and we put one of them on this side, and the other one on this side. And because the two sides are equal, if we sum up over x, then the two summations are also equal. And now we notice, by looking at the right-hand side, that pi of x prime doesn't depend on the summed x, or on the variable x, and so we can move pi of x prime out of the summation. And so this can now be rewritten as pi of x prime times sum over x t of x prime to x. Okay? And this summation over here, because t is a probability distribution over its outgoing, over the edges that are outgoing from x prime, is necessarily equal to 1. And so if we rewrite what we just proved in this one-line derivation, we just proved that the sum over x, pi of x, t of x to x prime is equal to pi of x prime, which is exactly the definition of the stationary distribution. So this is a one-line proof that a reversible chain gives me a chain that is reversible relative to a particular distribution pi necessarily has pi as its stationary distribution. Now, why is this a useful transition between the definition of the stationary distribution pi in terms of this equation down at the bottom versus this alternative definition of the stationary distribution pi? Because this definition down at the bottom involves the summation over what is in general an exponentially large space, whereas this one is, as we'll see in a minute, much more constructive in that it allows us to construct t so as to match pi. And so that is exactly the idea behind the Metropolis-Hastings, the definition of the Metropolis-Hastings chain. So how does the Metropolis-Hastings chain work? It starts out by saying, well, we want to move around broadly in the state space. And so we're going to have a distribution Q, which is kind of like a transition model. So this is my distribution Q, and Q is going to sort of roam freely over the state space. Unlike the Gibbs chain, it's not going to necessarily just take little local steps from one state to a state that's very nearby. It can look very far away and go into very distant parts of the state space. Now, that by itself, of course, is just going to give me a stationary distribution that has absolutely no relationship to the stationary distribution pi that I care about. And so what I'm going to have is a critic. The critic is the guy who says, whoa, wait a minute, you can't go there right now because this is not going to give you the right stationary distribution. So what does the critic do? The critic listens to the proposal that was made by the proposal distribution Q. So it says, oh, you want to go from x to x prime? Well, what is the probability with which I'm going to let you do that? So that's the acceptance probability. And that's a binary random variable for each x and x prime. What is the probability that we accept that proposal? So that gives rise to the following process. I haven't told you how to pick Q or A or anything yet, but let's just understand the process. At each state x, we sample a potential successor state x prime from my proposal distribution Q. So x, and we sort of have a proposal to go to x prime, and I denoted this using a dashed line. And now the acceptor says, do I accept that? And if the proposal is accepted, then I actually make that transition. And if the proposal is rejected, I just stay where I am. So what transition model does that give rise to? Because ultimately this just gives us a transition model from x to x prime. So there's two cases. Case number one is if x is not the same, so x prime is not x, that is x prime is a state other than x. Well, in this case, the only chance that I have of moving to x prime is if I proposed to move to x prime and if that proposal was accepted. So I need to multiply these two probabilities, and that gives me the expression, this expression for the transition. What about transition from x to x? Well, there's two different cases. Either I proposed a move to x and it was accepted, or x also gets the benefit of all of the transitions that were rejected by from other states that were proposed, but where the move wasn't accepted. And so what we have here is q of x to x, which we assume is always accepted. That's sort of one of the assumptions in this model. And then we sum up over all possible other transitions of the probability that they were proposed times the probability that they were rejected, which is 1 minus the probability that they were accepted. That gives rise to a transition model. So this is a general definition of a Markov chain, but as stated, there is no reason to expect it to have a particular stationary distribution. And so now this is where we bring back the intuition from the detailed balance equation, and we're going to use the detailed balance to construct an acceptance probability that has the property that we want. And so here's a detailed balance equation rewritten. And now let's write down, and we're going to assume in this particular example that x is not equal to x prime. And so we're going to, because this is trivial for the case x is equal to x prime, this equality always holds. Pi of x t of x is equal to pi of x t of x. And so let's look at the case x is not equal to x prime. And our goal is to construct A. So the goal is to construct A such that detailed balance holds for Q. I'm given Q, the setup is I'm given a proposal distribution Q, and now I'm going to pick A so as to make detailed balance hold. And if detailed balance holds for Q comma pi, then I'm going to, then that is going to guarantee that the process overall has the correct stationary distribution. So this is the equality that we want to have happen. And now let's go ahead and just define this as a constraint on the acceptance probabilities. So we have acceptance probabilities A occurring on both sides of the equation. So I'm going to move both A's to one side, move everything else to the other side. And so I get a constraint on the ratios between the acceptance probability from x to x prime and the acceptance probability from x prime to x. And that has to be equal to this ratio over here. And so I'm going to assume, without loss of generality, that this ratio, notice that this rate, we can decide this in any way that we want. We can either consider the ratio from x to x prime as the numerator or from x prime to x. I picked this one under the assumption that this is some value rho, sorry, this is equal to rho, which is less than 1. Oops. And so now, if we pick A, so now we need to pick the values of the two acceptance probabilities, x and x prime, so as to make this equality hold. And one simple way to do that is to take the smaller of the two, which we assumed was the numerator, and we make A of x to x prime equal to rho, and we make A x prime to x equal to 1. And that gives me immediately that this constraint holds. Now, of course, we could have picked these probabilities to be otherwise. We could have picked, for example, a x to x prime to be half of rho and a of x prime to x to be equal to half. But notice what that would do. That would just reduce the probability that our proposals are accepted, which would just make the chain move half as quickly because you end up staying at the same state twice as often as you would if the acceptance probability was higher. So these are in fact the highest numbers that we could possibly pick while still making this ratio constraint hold. And so that gives me, when you actually put it together as a general formula for the acceptance probability, it gives us this expression, which if you look at it, you'll see that it gives the right values for both x to x prime and for x prime to x. So that tells me how to pick A given Q. And the question is, what about Q? How do I pick Q? Well, that turns out to be the $64 million question. Picking Q is an art, and it's not an easy choice in many applications. But let's think about some conditions that Q must satisfy before we think about how to pick one. So one condition on Q is derived simply by looking at the form expression for A. And we can see that this here involves a ratio And if you have a ratio, then one condition is that you better not have a denominator that's equal to 0. And so one of the things that we must guarantee regarding Q in order for this to be a valid set of acceptance probabilities is that Q itself must be reversible in the following sense. That is, if the numerator is greater than 0, then the denominator is greater than 0 and vice versa. That is, if you can propose a step from x to x prime, you better be able to propose a step from x prime to x with non-zero probability, which guarantees that this ratio is always well-defined. Now, the problem with this constraint on Q is that it actually induces a tension in the design of Q. Now, on the one hand, you'd like Q to be very broad. So if you're at this state over here, you'd like Q to sort of go really far away from the current state. Because the further away you can go, the faster you move around in the state space. You don't want to stay local. You don't want to make the same mistakes that the Gibbs chain does by staying very near to the current assignment. You want to move around quickly, and that improves mixing. On the other hand, if you look at the implications that this formula has when the proposal distribution is very broad, and so that you have one state that, for example, has low pi, and the other state has a very high value of pi, which is what you get when you move around from a hilly part of the space to a low part of the space. You have very big differences in terms of the height of the two stationary. So what I'm drawing here is the height of pi, and this is my state space x. And if I move around very far, I'm liable to get into situations where pi of one state x might be considerably larger than pi of x prime. And if you think about what that implies regarding the acceptance probability can get very, very low, which in turn implies slow mixing again, because you might be taking very global steps, but you're taking very few of them. And so this is a real sort of tension in the design of proposal distributions Q. So let's take an example of a Markov chain where proposal distributions can make a very big difference. And this is a problem that you wouldn't necessarily immediately think of as a graphical model, but can be formulated as one, and it's a matching problem. And we'll see it in other settings as well. So here we have a bunch of red dots, as we see over here, and we have a bunch of blue dots, and we want to match the red dots to the blue dots. And there's some sort of preference function. So these edges over here are annotated, I'm going to mark in green, are annotated with some kind of weights that tell us how happy is this red dot to be matched with this blue dot. And this happens a lot, for example, in various correspondence problems where we're trying to match sensor readings to objects, for example, in a tracking application. It also happens in image problems where you want to match features in one image to features in another. So it's a very common problem. So one formulation of the matching problem as a graphical model is that we have a variable xi for each red dot. So the red dots are going to be the variables. The blue dots are going to represent values. And we're going to have that xi is equal to j if I match I to j. So that can now be written as a probability distribution over a space. And so we can consider the probability of an assignment of values to variables. And we're going to say that, first of all, it has to be a matching. So if we don't have that every red dot is matched to a different blue dot, that's a probability 0 assignment. So this would be the case if you had two red dots that matched to the same blue dot. And otherwise, we're going to define some kind of weighted combination of, it's going to be an exponential of the sum of the quality of the matches between the red dots and the blue dots. So we're summing up the quality of the edges that participate in the matching. So for example, if this is my matching over here, and notice that I didn't get to match all the red dots. That's, well, actually here, I'm going to match all the red dots. So now we have a matching for each red dot, we assign the blue dot as a value, and now the overall quality is the total sum of the quality of the matching, and that can be exponentiated to define a probability distribution. So, and we're going to represent these qualities visually in this example as distances, so that we're going to assume, for example, that this red dot prefers to be matched to this blue dot more than it prefers to be matched to this further away blue dot. So one can imagine running a Gibbs sampling distribution on this model by taking a variable and say one of the red dots and picking a new value for it that is a new blue dot that it wasn't matched to. This is going to change things very, very slowly because most of the blue dots are going to be taken by a different red dot. And so those assignments where a red dot is matched to a previously taken blue dot are going to have very low probability, 0 probability, in fact. And so those are going to be impossible. So the only thing I can do is I can make the red dot match a different blue dot, match one of the unmatched blue dots. And that's going to take a very long time for things to change. Here is a different way of doing this, which is the Metropolis-Hastings, which is one way of constructing a proposal distribution and using Metropolis-Hastings, and that's called an augmenting path proposal distribution. So what that does is, let's assume that this is my current matching. I'm going to define the following proposal. I'm going to pick one of the variables xi, say this one, and I'm going to say, I'm going to pick another value for it, pretending that everything is available. So I'm going to ignore the fact that this guy is already matched. I'm going to pick this one. I'm picking it probabilistically, so I could have picked a different one. I could have picked the same one that I was matched to before. I could pick a further away one, but say I picked this one. Well, now this guy, poor guy, this one is unmatched. This red guy over here. So it has to pick a new partner. And so say it picks this one. This red guy is unmatched now, and so it might pick one and say it picks this one. And that leaves me with this red guy and say this red guy picks this one, and notice that now I have a new legal matching. I've closed the loop, and I've defined what's called an alternating cycle, where basically I can switch all of the black edges to green edges, and that gives me a new legal matching. And that's my proposal. And with a little bit of a numerical calculation, one can figure out the acceptance probability for this proposal distribution. And it turns out that it's actually a really good proposal distribution. So let me show you some examples on the next slide. So this is the results on the chain if I just apply Gibbs sampling. And you can see over here 4 chains. So the 4 colors represent the 4 chains. And what you see on the x-axis is number of steps. And on the y-axis is some kind of statistic that I'm tracking in order to gauge whether the chain is mixing. As it happens, it's the probability that the first red dot is matched to the first blue dot, but it doesn't matter. Any statistic would have illustrated the point here. And you can see that there's a lot of long-range fluctuations in the chain. That is, the probabilities change over time. The probabilities, by the way, are computed over windows of size 500 from the samples in that window. And you can see that the chain takes a long time to move from one region of the space to the other. The proposal distribution that I just showed you by contrast is totally different. You can see that the probabilities are almost totally flat, and that there's basically all four chains are the same, and there's almost the same, and there's very little change in windows over time. And there's an even better proposal distribution that I didn't show you that modifies the augmenting path by just a little bit, and that gives you effectively perfect mixing across the entire time. If we look at the other metric that we defined for evaluating mixing, we can compare the probabilities of these different statistics of different statistics across the two chains. So, for example, this might be just, for example, the red chain, and this might be the green chain. And what we see here are the statistics that you get for different kinds of probabilities, for the probability that this variable is matched, sorry, that this dot is matched to that dot, for example. And you can see that the Gibbs chains, the estimates that you get are very noisy, and the different chains give you divergent estimates. The second Metropolis Hastings, sorry, the first of the Metropolis Hastings gives you things that are almost on the diagonal, and here things are effectively exactly on the diagonal, perfect mixing. So to summarize, Metropolis Hastings is a very general framework for building Markov chains so that they are designed to have a particular stationary distribution. It requires that you come up with a proposal distribution, and that proposal distribution needs to have certain properties in order to be valid. But once you give me such a proposal distribution, the detailed balance equation, which is this nice simple equation, tells me how I can construct the acceptance distribution so as to enforce the fact that we get the right stationary distribution. So this is great in some ways because it gives us this huge flexibility in designing proposal distributions that explore the space quickly and move around to faraway parts of the space. But as we saw, picking the proposal distribution is actually an important design point, and it makes a big difference to performance. And there isn't like a science of how you should do this effectively. And so this is something that is really an art and requires a non-trivial amount of thought and engineering.